Let's continue now. In the last two videos, we have looked at Noetherian rings. These are rings where every ideal is finitely generated, or alternatively, these are rings where every ascending chain of ideals stabilizes. We looked at various examples of Noetherian rings that we know, integers, polynomial rings over fields in one variable, even in polynomial ring in one variable over the integers. And we also looked at a couple of examples of rings that are not Noetherian, a polynomial ring in infinitely many variables or a field, for example, or the ring of continuous functions from real numbers to real numbers. And we also observed that if a ring R is Noetherian, any quotient ring R mod I is Noetherian for every ideal I. So now the main theorem in the study of Noetherian rings is called the Hilbert basis theorem. So that's on your screen now. It says that if you have a ring which is Noetherian, then a polynomial ring over it in one variable is Noetherian also. Okay, so let's prove this, and using this, of course, we can apply induction to prove that polynomial ring in finitely many variables over a Noetherian ring is also Noetherian. So after proving the theorem, I will remark on how to apply it. So this is the proof of Hilbert basis theorem. So today's video is dedicated to proving Hilbert basis theorem. So we are going to use the original definition of Noetherian rings, and we will show that if I is an ideal in Rx, then every ideal it is finitely generated. So let's start with that. Let I be an ideal, so an arbitrary ideal. So remember, the goal is, so I'll write that here, goal is to show I is finitely generated. So that means we have to exhibit a finite set of elements of I which generate it as an ideal. Okay, so what we'll do is the following. So among all elements in I, remember what are elements in I? These are polynomials with coefficients in R in one variable x. So elements of I, indeed elements of Rx itself, are polynomials in X with coefficients in R, right? These are how elements of the polynomial ring look like. So in particular, they are written in mathematical symbols, they are of this form. Where X is of course a symbol, A, N through A, 0 are elements of R, and N is a non-negative integer. So N is 0, 1, 2, 3 and so on. Okay, so these are elements of R. So now I, being an ideal, consists of some such polynomials. If I is 0, if I is the 0 ideal, then it is certainly finitely generated. So we may assume I is not the 0 ideal, right? 0 ideal is certainly a finite ideal. In fact, it consists of only the 0 element. So it is surely finitely generated. So we may assume I is not 0. That means it contains non-zero polynomials, and for every non-zero polynomial we have what is called the degree, right? So what is the degree of this? So if an is non-zero, we always assume that, otherwise we will not even write that term. So degree of this is n. So this is the largest power of x that you see in the polynomial. So this is defined for every non-zero polynomial. So we look at degrees of all non-zero polynomials in x, in I. So choose f1 to be the following. Choose f1 to be a polynomial in I which has least degree. So choose f1 to be a non-zero polynomial, f1 is non-zero, to be a polynomial in I which has least degree among all elements, all of course non-zero elements, so that I will forget maybe sometimes, among all non-zero elements in I. Okay, so of course you can avoid you separating out non-zero elements by declaring the degree of the zero polynomial to be 0. So I want to take the polynomial which has least degree among all non-zero elements. So I remove 0 element. What am I doing? So I of course has infinitely many elements typically. So we look at degrees of each non-zero element of I. So these are all non-negative integers. It can be 0. For example, if I contains a non-zero constant, its degree is 0. So potentially 0, but they're all non-negative integers. So among all these non-negative integers, there will be one which is smallest. Non-negative integers have this property that any set of non-negative integers has a least element. So we identify that. Maybe it is 3. Maybe 3 is the least degree of polynomials in I. There would be lots of polynomials of degree 3 in I perhaps, but I am just going to pick one of them. So F1 is not unique definitely, but there is some such polynomial. This means, so I am going to spell this out because this is an important fact, important property of how we are choosing F1. So this means that if F is any non-zero element, then degree of F is greater than or equal to degree of F1 because of the choice of F1. Maybe it is equal to degree of F1. That's allowed, but it cannot be strictly smaller, because if it is smaller, then the degree of F1 is not the smallest degree of an element in I. It has smaller degree element, so we would pick that or even something smaller. So if F is in I and it is non-zero, then degree is at least degree F1. Okay, so now we have chosen the first element. So like in a previous proof, in the previous video where we were doing proving that ascending chain condition implies Noetherianness, we are going to construct an infinite chain sequence of elements of I, and this is our first element. F1 is the first one. Now consider the ideal generated by F1. So of course it is contained in I. Clearly, so clearly the ideal generated by F1 is in I, because F1, remember, is in I. So I emphasize that here. F1 is in I, so the ideal generated by F1 is in I. If it is actually equal to I, then we are done. We are done because what is the goal which I wrote here? We want to show that I is finitely generated. If I is actually generated by F1, it is generated by a single element, which is what we want, which we want in fact a finite set of generators. So if F1 is I, we are done. If not, in other words, if the ideal generated by F1 is not I, then I is of course strictly bigger, because certainly it contains F1, but if it is not equal, it is strictly bigger. That means, yet another way of saying that is that the set I minus F1 is not empty. In other words, elements in I that are not in F1 is a non-empty set. There are elements in I that are not inside the ideal generated by F1. Now choose F2 to be exactly as before. How did we choose F1? F1 to be a least degree polynomial among all elements in I. Now I don't do it among all elements in I, but I choose F2 to be a least degree polynomial in I minus F1. So this means among, so that is among all polynomials in I minus F1, F2 has least degree. So said another way, if some other polynomial f is in I minus F1, its degree is at least the degree of F2. So again remember, F2 is not unique with this property. There is perhaps lots of polynomials which have least degree, but I am going to just choose one. I don't care how I choose this. I just choose F2 to be that. Now we continue. If F1, F2 is equal to I, we are done again. Meaning we have shown that I is finitely generated by these two elements. Otherwise, we continue. And how do we continue? We simply take F3 to be a least degree polynomial in I minus F1, F2 now. Right? If I is not equal to the ideal generated by F1, F2, it must be strictly bigger than the ideal generated by F1, F2. That means there are elements in I that are not in the ideal generated by F1, F2. Lots of them, infinitely many maybe. But I am going to choose the one which has the least degree. And of course, everywhere I am taking non-zero, but that's I don't need to write that here because 0 is in the ideal generated by F1, F2. So only elements in I minus F1, F2 will be non-zero. So we continue like this. To obtain a sequence of elements F1, F2, F3 and so on in I. And just to repeat for you the procedure of how to choose these. Suppose you have chosen 100 of them. F100 is chosen. How do you choose F101? You choose it in the following way. You look at the ideal generated by F1, F2, F3 up to F100. This is the finitely generated ideal which sits inside I. So if it is equal to I, we stop, we are done. There is no more work to do. But if I is strictly bigger than the ideal generated by F1, F2, F100, there are non-zero elements in I minus the ideal generated by F1, F100. Among all those elements, we pick a polynomial with the least degree, which we call F100, F101, and then we continue. Remember that if this process stops at any point, we achieved our goal, which is that I is finitely generated. So we have to rule out the possibility that this process continues forever. And we have now constructed this, and I will only remark now, this is something we will use later. Note that degree of F1 is less than degree of F2, less than degree of F3, less than degree of F4 and so on. So degrees keep increasing. Why is that? Because when you are choosing F1, you are choosing a polynomial with the least degree, right? So in other words, when I wrote earlier, if F is any element of I non-zero, then degree of F is greater than or equal to degree F1. F2 is one such element, right? Because F2 is being chosen later. So degree of F2 will be greater than or equal to F1. Now F3 will be chosen after F2. So if F3 has strictly a smaller degree than F2, we would not have chosen F2 in step 2. So degrees keep increasing like this. Okay, this is very easy point. Think about it for a minute, pausing the video. Think about it for a minute if it's not clear to you. At each stage, we are picking picking a polynomial with the least degree. And if we have chosen F100, F101 is to be chosen in the next step. So if F101 has smaller degree than F100, why would we choose F100 now? We would have actually chosen something which has a smaller degree. So F101, which is actually chosen at a later stage, will have a bigger degree than F100. When I say bigger, it could be equal, but it will not be less than. It could be less than or equal to. We have this relation. Now, so far we have not used the hypothesis. Remember, we can't in general prove that Rx is Noetherian for arbitrary rings R. We want to use the fact that R is Noetherian, and that's done in the following way. Okay, so what we do is, let AI, so now I have constructed F1, F2, F3 and so on. So we are going to work with these now. Let Fi be the leading coefficient of Fi. So we do this for every I. What is the leading coefficient? So remember, I will simply say this by saying LC of Fi. LC of Fi is simply the coefficient of the largest degree term you have. So LC of 2x squared minus 3x plus 1 is 2. LC of minus x cubed plus 3x minus 8 is minus 1. Okay. So leading coefficient is simply the coefficient which is in front of the largest power of x in your polynomial. So certainly AI is in R, and this is where we will go to R now and use the hypothesis. So we have now A1, A2, A3 and so on. These are all elements of R. So we have an infinite sequence, potentially infinite sequence of polynomials, and we are now forgetting the polynomial except the leading coefficient. We take the collection of leading coefficients and define now J to be the ideal generated by all these leading coefficients. So this is an ideal by definition, right? I am not taking the set of these leading coefficients, of course that's certainly not an ideal. I am taking the ideal generated by. So this is the ideal, this is our notation, remember, generated by A1, A2 and so on. Now by hypothesis R is Noetherian, correct? This implies J is finitely generated. Because R is Noetherian, every ideal of R is finitely generated, in particular J is finitely generated. Now I claim that we know that there is in fact a finite set of generators, but I can assume that J is actually equal to A1, A2, AN for some n. Okay, this is a little exercise for you. What we actually get from the statement that J is finitely generated is that there is a finite set of generators. They need not be to begin with. Maybe the finite set of generators you are given are not A1, A2, A, they are not in net, they are not actually AIs. But you take any of the generators, so maybe I'll just quickly write the reason. So reason for this implication is that let J be generated by, let's say B1 BS, okay, B1 through BS are inside J, right? We know that J is finitely generated, that means J belongs, J is generated by some finitely many elements of it contained in J. Now we know that A1 through AN and so on, I mean infinitely many AIs, potentially infinitely many AIs generate J. So since A1, A2 and so on generate J and B1 is in J, let's use first B1, we can write B1 as some R1 A1 plus, I don't know what, actually it need not be 1. So R1 AN1 plus R2 AN2 plus RK ANK. Remember that even though J has infinitely many generators, any particular element of J can be written as a finite sum like this. Similarly, we can write each BI in terms of AI or A1, A2. The point is, maybe B1 will require the first 1000 ANs, B2 requires first 1 million AIs, B3 may require first billion, but I don't care. I will, because B1 through BS is a finite set, I will look at all the AIs that appear in B1, all the AIs that appear in B2, all the AIs that appear in BS, and look at the largest index of A that appears in those and take those up to that index, A1, A2, AN. So the point is, J could be maybe generated by 10 BIs, but if I include AIs, maybe I have to go up to 1 million, because maybe B10 requires up to a million, but I don't care about what N is. It doesn't matter to me if n is very big. I am not looking to find an efficient set of generators. I am only interested in finding generators so that I can say first n of them generate j. So this is just an argument to explain that. Again, please pause the video and think about it if it's not clear to you, and you can ask questions if it's something is not clear to you still. Another way to see this is, we can also argue like this. So we can consider the chain like this. So A1, A2, A1, A2, A3 and so on, right? So this chain, this ascending chain stabilizes because it's an ascending chain of ideals in a Noetherian ring R. So it stabilizes, that means it is equal beyond some point, they are all equal, but they must all equal j, because if it is not equal to j we would have continued, okay? So this is another argument to show that j is equal to the ideal generated by A1 through An. Now finally, to finish the proof, I claim that I, now go back to the ideal I in Rx, in fact will be generated by, remember that, just to recap the proof, I have started with an arbitrary ideal in Rx, I is an arbitrary ideal in Rx, I have constructed an infinite sequence by describing the by the process described at the beginning of the proof, and I have taken the leading coefficients each of them. The ideal of the leading coefficients, which is actually an ideal j inside R, is finitely generated. So it's finitely generated in fact by the first n leading coefficients. Now to finish the proof, I am claiming that I is in fact generated by those n polynomials. We don't need to continue, and the proof of this is the following. Remember how we were constructing these fi's. If I is not equal to f1, f2, fn, we would have chosen fn plus 1. Remember the construction of fi's. If the ideal generated by the first n of them is not equal to I, we would have chosen fn plus 1 to be a polynomial of least degree among all elements of I minus the ideal generated by fn. Okay, so now we have f1 through fn which is not equal to I, and then we continue the process that I described at the beginning of this proof. So fn plus 1 has least degree among all elements. But now let recall an plus 1 is the LC of fn plus 1, because I have defined ai to be LC of fi for every I. But this belongs to j. Remember, j is ideal generated by all the leading coefficients. So an plus 1 belongs to j, but I have just argued using the Noetherianness of R such that a1 through an generate j. So an plus 1 is in the ideal generated by a1 through an. So we can write an plus 1 as summation bi ai I equal to 1 to n. So just for clarity I will write it like this. And what are bi's? Where bi's are some arbitrary elements of R. I don't care what they are just elements of R. Now I have forgotten the polynomial ring. I am actually now arguing inside the ring itself, the coefficient ring. Because j is generated by this, an plus 1 can be written like this. Now I am going to define a new polynomial g as follows. So g is defined as b1 f1 times x power m1. I will tell you what m1 is. b2 f2 x power m2, and all the way up to Bn Fn x power Mn, where Mi is degree of Fn plus 1 minus degree of Fi, okay, for each I from 1 to n. Okay, so remember I remarked earlier that degrees of Fi's keep increasing. Degree of F1 is less than equal to degree F2, less than equal to degree F3, less than equal to degree F4, and so on. So these are all non-negative integers. So note that Mi is greater than or equal to 0 for all I. So I can in fact consider x power m1, x power m2, x power mn. These are, if they were negative, of course this will not be a polynomial. X power minus 1 is not allowed inside a polynomial. But because mi's are non-negative, I can put a coefficient exponent like that and it is a polynomial. So f1 times x1 power m1, f2 times x power m2, fn times x power mn. What kind of polynomial is G? So first note the following about G. We have first that G belongs to the ideal generated by f1, f2, fn. Right? That's obvious because G is actually written as f1 times something plus f2 times something, right? Because f1 is here, f2 is here, f1 is here, so it is f1 times something plus f2 times something plus fn times something. So it is in the ideal generated by f1 through fn. Moreover, we also know that leading coefficient of G is equal to what? What are the degrees of these terms? So whatever is the leading coefficient of f1, so I am going to separately look at each term that appears in G. So let's look at this term, this term, this term separately. So remember that the reason I am multiplying by x1, x power m1 is so that the degree of x power m1 times f1 is actually equal to degree of fn plus 1, right? Degree of f1 is potentially smaller than degree of fn plus 1 but I am providing the remaining x. So by multiplying by x power m1, this term now will have degree equal to degree of fn plus 1. Okay. Similarly, this term now will have degree equal to degree fn plus 1. This term will have degree equal to degree fn plus 1. So what is the leading coefficient of B1 through of G? So I can certainly write this as summation LC of Bi Fi x power mi. So you have a sum of polynomials. The leading coefficient, all these polynomials have the same degree, right? Because this degree is degree fn plus 1. This degree is degree fn plus 1. This degree is degree fn plus 1. So the leading coefficient of the sum is simply the sum of the leading coefficients. Leading coefficient of G is the leading coefficient of the first one plus leading coefficient of the second one plus leading coefficients of the third one. But now continuing here, what is leading coefficient of this? This is summation leading coefficient of, I can pull out Bi, right? Bi is actually a constant term. Bi is an element of R. So this is summation. So of course summation goes from 1 to n. Summation from 1 to n. Bi times leading coefficient of Fi times x power mi. Correct? But leading coefficient of Fi times x power mi, see Fi could be, I am just giving an example. So Fi could be some A5, x power 5 and so on. So not A5, let us say C5, x power 5 and C4, x power 4 and so on. So the leading coefficient is C5. When I multiply by x mi Fi, I get C5 x 5 plus mi C4x4 plus mi plus and so on. So the leading coefficient does not change from fi when I multiply by x power mi, because the leading coefficient of x power mi is 1. In general, when you multiply two polynomials, leading coefficients get multiplied also. Here leading coefficient of fi mi is just leading coefficient of fi times leading coefficient of x power mi, but leading coefficient of x power mi is 1, so I can omit this. So bi times leading coefficient of fi. But what is leading coefficient of fi? Leading coefficient of fi is by definition ai. So I have summation bi ai. But remember, what is summation bi ai? It is actually an plus 1. So this is from before, this is actually an plus 1. So all this calculation proves that leading coefficient of G is an plus 1, which remember is also leading coefficient of fn plus 1. Now consider fn plus 1 minus G. So you have two polynomials, but their leading coefficients are, so they are first of all equal degree. Degree of f is equal to degree of fn plus 1 is equal to degree of f, and the largest degree in each of them is same, and moreover the coefficients are also same. So when I subtract this, the degree of fn plus 1 minus G is strictly less than degree fn plus 1, right? Because you have two polynomials as an example. So let's look at an example. So you have fn plus 1 could be 3x power 7 minus and so on. So minus 4x power 6, I don't care what it is. What we know is that G, so this is just an example, G also has the same degree and has the same leading coefficient. So but other terms may very well be different. What now I am doing is fn plus 1 minus G. So when I do that, this goes away. So what I have is actually minus 11x power 6 and so on. So the degree of this drops. What I mean is, when I subtract one polynomial from another polynomial and these two polynomials have same degree and same leading coefficients, the first term will cancel out, and what you are left with has smaller degree. But this now tells me that degree of this is strictly less than degree fn plus 1. So that means, and now recall how we chose fn plus 1. We chose fn plus 1 to be a least degree polynomial in I minus the ideal generated by fn. Right? We chose this to be the least degree polynomial, and degree of fn plus 1 minus G is strictly less than degree fn plus 1. So in fact, this tells me that hence fn plus 1 minus G is inside f1 through fn. Right? Is that clear? Because fn plus 1 minus G is certainly an element of the ideal, because everything is happening within the ideal I. So fn plus 1 minus G is an element of the ideal if it was not in the ideal generated by f1 through fn. So suppose this is not true. Suppose what is in this box is not true. That means this polynomial fn plus 1 minus G is not in the ideal generated by f1 through fn. That means it is in I minus f1 through fn. Because if it's not in the ideal generated by f1 through fn, it is in its complement. That means it's inside this. But it then, because it has smaller degree than fn plus 1, that violates how we chose fn plus 1, because that was supposed to be a least degree polynomial in this complement. So there is no choice but for this to belong to this. But G already belongs to right? G belongs to this, because the way I defined G, it certainly belongs to, I commented that here. G is already written as a linear combination of f1 through fn. So G belongs to this. Now we can write Fn plus 1 as Fn plus 1 minus G plus G. This belongs to this belongs to F1 through Fn. This belongs to F1 through Fn. G by definition belongs to this difference belongs to this because of this argument. So this belongs to F1 through Fn. But this is a contradiction. But this is a contradiction because if Fn plus 1 belongs to this, we would not choose this. Fn plus 1 is chosen to be a least degree element in the complement. In particular, by definition, it doesn't belong to F1 through Fn. So this is a contradiction. So the proof is complete. So we have proved that Rx is Noetherian. Okay, so this is the Hilbert basis theorem. The proof is not difficult, but it could be confusing if you are seeing this for the first time. So please go over this video as many times as you have to make sure that you understand this argument. This is a very nice argument to show that if R is Noetherian, the polynomial ring in one variable over R is also Noetherian. So corollary is, if R is Noetherian, this implies that the polynomial ring in n variables is also Noetherian. The Hilbert basis theorem actually talks about adjoining one variable, but I get the case of finitely many variables easily, because if you remember how we talked about polynomial rings for the first time, if I do this, our polynomial ring in one variable, n variables is like this. It is actually can be thought of as a polynomial ring in Xn with coefficients coming from, this is just a matter of perspective, right? Here the variables are x1 through xn, coefficients are in R. Here variable is xn, coefficients are in this ring. But now this becomes a polynomial ring in one variable over this ring. So it suffices to check R adjoined is Noetherian. Because by Hilbert basis theorem, if this is Noetherian, by adjoining an extra variable, this is Noetherian, and we keep doing this by induction, we get this. Okay, so this is clear, right? So all I am saying really is going from R to bigger polynomial rings. R Noetherian implies Rx1 Noetherian by the statement of Hilbert basis theorem. So Rx1 adjoined x2 is Noetherian. So this is a ring, it's a Noetherian ring, adjoined an extra variable is Noetherian, but this is nothing but, this is just different notation for the same ring. So polynomial ring in two variables is Noetherian, and you keep going. As long as you are only attaching finitely many variables, you get Noetherianness. Remember, of course, that if you attach infinitely many variables, we know that it is not Noetherian. And finally, I will end the video with this corollary. If R is Noetherian and I in R polynomial ring in n variables is an ideal, this implies the quotient ring of the polynomial ring Rx1 through xn modulo I is also Noetherian. This is because R is Noetherian. By the previous corollary, the polynomial ring is Noetherian, and by a proposition that we did in the previous video, any Noetherian ring modulo an ideal is also Noetherian. So this is an important statement. So in a lot of most of the course, we will only deal with polynomial rings and their quotients among other rings, but this is an important class of rings for us, and these are all Noetherian because of Hilbert basis theorem. So in this video, we have proved a very important theorem. This is one of the most important theorems in the whole course called Hilbert basis theorem. And from next video onwards, we are going to study a special class of rings two special classes of rings called principal ideal domains and unique factorization domains. Thank you.